All right, hello, welcome back to another math accounts meeting. Today we're going to start 2012 Math Accounts Nationals. We're on sprint number 1. Hiram is helping his little sister write her integers from 1 to 50. He suggests that they take a break after she has written her 33rd digit. What was the last 2-digit number that Hiram's sister wrote before they took the break? Okay, so they're writing integers starting from 1, and we're counting how many digits they write, and after she's written her 33rd digit, they take a break, and we want to know what's the last 2-digit number they wrote before they took the break. Okay, so we should figure out where this 33rd digit is. So if we start writing from integer 1, and we're continuing integers from here, all the 1-digit integers that we write, it's going to take up 1 digit, right? So when we write the integers from 1 through 9, we're gonna use 9 digits in total, right? So like after we've written this, then how many digits left do we have to write? We had to write 33 minus 9 more digits, right? And this is just gonna be 24. So now we just count 24 more digits. So after we write the digits 1 through 9, we're going to start on the 2-digit numbers. So each 2-digit number here, it's going to take up 2 of our digits. So 10 is going to take up 2 of our digits. And then after we've written 11, we're going to have written 4 digits. And after we've written 12, we're going to have written 6 digits. And we want to find the 2-digit number where we've written 24 digits, right? Because that's how many more digits we have to write, and that will be our last 2-digit number that we will write before we take the break. Okay, and then so this is just like if we're at 9, we're at 0, and then you can just scale this progression like down by 2, right? So like 0, 1, 2, 3, and we want to reach 12. And then if we scale it down by 2, then it just increases by 1, and then we can just see that this always has a difference of 9. So then we just add this by 9, and we'll get 21. There's also different ways you can do this. I mean, you can just find like how many integers it takes for you to count from 2 by 2s to 24, and then you also get to 21. Yeah, I just did it like that, but yeah. Okay, so then 21 will be the last 2-digit number that we write, and that will be our answer. And yeah, that's your answer. Okay, number 2. The 660 students at Mandelbrot Middle School voted on their choice for favorite among 6 mathematicians. The table shows the results of the vote. Finn made a circle graph to represent the data in the table. In degrees, what is the measure of the central angle of the sector that represents votes for Gauss? Okay, well, we're making a circular graph of all of this, and we want to find the angle of the sector. The angle of that sector is just going to be it's just going to be the proportion of this votes to the total, like a fraction, and we're going to multiply that by 360 degrees, right? So I mean, you guys should already know that, right? And it makes sense, right? Because like if you have a proportion of 1, then it goes all the 360 degrees, and it scales just linearly with proportion. So like if it was 101 over 1/360th of the thing, then it would just be a sector of 1 degree. It's fine if you're late, Sean. Okay. Yeah, and we're just on problem 2, so it's fine. Okay. So then we just want to find the proportion of Gauss votes to the total number of votes and multiply that by 360 degrees. So we're gonna have to find the total number of votes. Oh, and it says the total number of votes is 660. So the proportion of Gauss votes to the total votes is going to be 121 over 660. Want to simplify this? You see top and bottom have 11. So then we have 11 over 60, and then we just need to multiply this by 360. 360 is 6 times 3, or sorry, 360 is 6 times 60. So then this will equal 66 degrees. And that's our answer. What is the sum of all positive integers n such that root 3 is less than or equal to n, which is less than or equal to root 99? So root 3 is going to be, root 3 is less than root 4, and root 4 equals 2, right? And we know between root 3 and root 4, there are no integers, right? Because root 1 is 1, and this is less than root 3, right? So there's, and this is 2, right? So there's no integers here. So basically, we can just substitute root 4, which is 2, into there. So then 2 is less than or equal to n is less than or equal to root 99. So basically, I've pushed this lower bound up, and I can do that because I know that there are no integers when I push this up. Like I'm not missing any integers. And then with this root 99, so we can see that 10 will be out of bounds of this root 99, right? Because root 99 is less than root 100, which is equal to 10. So that means the highest integer that we can have will be 9, right? So then we just have 2 is less than or equal to n, which is less than or equal to 9. And then we just want to find all the, or the sum of all the positive integers that are in here, which is just 2 plus, 2 plus 3 plus dot 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 all the way to plus 9. And then this is just the arithmetic sequence. We're going to take the mean, which is 11 halves. It's first and last. You add it up, and then you take it over 2 times the number of integers that are here, which is 8. And then this will be 44. So yeah, that's your answer. Okay. 10 items have the following weights in pounds: 2, 3, 5, 5, 6, 6, 8, 8, 8, and 9. The items are then divided into 3 sets of 20 pounds each. How many sets contain an 8-pound weight? Okay, so we have 10 weights. We need to divide them into 3 groups so that each group has 20 pounds. We want to find how many sets contain an 8-pound weight. So I think the only way you can really do this is just to try to sort them so that each of the groups has 20 pounds, and then you find like how many 8s or how many sets have an 8. I don't really see any other way you can do this. Like anything you wanted to say on that, Bill? I don't know.
No, I mean that's how I did it too. Just divide them, find a way that it works. Yeah, maybe you could do something with like modulus, but I don't know.
I don't know. Yeah, that's just too weird. Yeah, just put them in the groups, and then count how many 8s, or count how many sets of an 8. And so you can try sorting them. We've already found the solution though. It was like, so you take 9, 8, 3, so that's 20. You take 8, 6, 6, that's also 20, and then the rest is what? 8, 2, 5, 5, and that's also 20. But this didn't take too long. It maybe took like 1 minute or so for me to get these groups. So yeah, just find the groups, and then now count how many count how many sets have an 8, which is there's an 8 in each set, so that means we're gonna have all 3 sets have an 8, and that should be your answer. Yeah. Okay, the sum of 5 different positive integers is 80. What is the largest possible value of the second largest number? Okay, so we're summing 5 different positive integers, and we're summing it to 80. If we want the second largest number to be as large as possible. We want all the other numbers to be as small as possible, right? Um, now we can't do much about like the largest number because it is the largest number. So we can't decrease it because if we decrease the largest number, then the second largest number is going to be decreased. So basically, we just have to decrease the other three integers, and we want them to be as low as possible. So the largest and the second largest can be as large as possible. And so the smallest positive integers that we can use is 1, 2, and 3. And then so we have some other two integers, and then all this sum to 80, right? So then because this sums to 6, then our two remaining integers sum to 74. And all these positive integers are different, right? Now the average of 74 is going to be 38, but we can't have 38 because these are the same integer. So we're going to have to increase this one by 1 and decrease this one by 1. So that this is still the largest and this is still the second largest. And then this is the largest, second largest number that we can have. So 37. Oh, wait, no. Wait. 70. Wait, my bad. Okay, wait, sorry. 74, the average is 37, not 38. Okay, so then we increase this by 1 and decrease this by 1. And then this is our largest. And that's our answer. It was just my mistake. Okay. From the time a shop opens at 10 a.m., one customer enters the shop every 15 minutes until the shop closes at 7 p.m. There's a one-third chance that the salesman will convince the customer to buy a widget. The shop owner makes a profit of $6 on each widget sold. What is the most the shop owner can pay the salesman in dollars per hour to exactly break even? That is, what hourly rate will make the amount paid to the salesman equal to the total amount of income from widget sales. Okay, so basically in this problem, we're getting some money at some rate from this sale of widgets, and we want to pay the salesman equal amount of money to this rate so that they break even. You can do this in you can do this in two ways. You can either go through the whole time interval, find like your total profit, and then divide that by how long your time interval was, or you can just do it by like a 1 hour rate. It's probably better to do it by a 1 hour rate because then I don't know, it's just less steps, right? So let's think of a 1 hour interval. In a 1 hour interval, because one person comes every 15 minutes, we're gonna have four people that come, and then because we have a one-third chance that the salesman will convince each customer to buy a widget, this is like an expected value of 4/3 customers buying the widgets, and then we multiply this by $6 to find the expected profit that we get per hour, and this is equal to $8. So then we get an expected $8 profit every hour, and it tells us that we want to pay the shop owner so that this breaks even. So then we pay them $8 per hour. So that's our answer. Yeah, that's your answer. And so the time interval here was unnecessary. And the answer says they accept $8 like this or 8.00, but I think it would be safer if you say 8.00. I think they might only accept 8.00 on newer year math counts tests because this one is like 2012. Right, Bill? Do you know if they only accept like two decimal place money stuff?
I think you should just put .00 just to be safe. I don't think they're gonna count it wrong.
Okay. Yeah, I would put it to be safe. I'm not sure if they accept both, but it'd just be safer if you put dot zeros here. Okay. I know in like number sense UIL in calculator or yeah calculator UIL they don't accept if you don't have it to two decimal places, or if you do UIL it's only in Texas, but yeah. Okay. um Number 7, the odds against event A occurring are 3 to 1, and the odds in favor of event B occurring are 3 to 5. What is the probability that at least one of these independent events occurs? Which special answer is a common fraction. Okay. So we have the like odds of A and B occurring, but we want to put this into a probability fraction because that's just easier to work with and stuff, right? Okay, and if we have the odds against event A occurring are 3 to 1, to get the odds in favor of event A occurring, we just reverse this. So odds in favor of event A is 1 to 3. And then to convert this into a probability, we're going to put our 1 on top, so our left number here. And on the bottom, we're going to put the sum of both numbers, so 1 plus 3. So then the probability that A will occur is then 1/4. And then B, we already have it as in favor. And then so the probability of B occurring is 3 over 3 plus 5, which is 3/8. And you can just derive this from thinking of how odds work, right? So odds is always like this is like you're in favor of B, and this is like you're against B. And if you add them, you just get the total portion. Okay, so then our probability of A is 1/4, our probability of B is 1/4, or sorry, 3/8. And now we just want to find what is the probability that at least one of these independent event occurs. How we can do that is we think of, we look at the probability of A first. There's an initial 1/4 chance that we just, that event A just occurs and then we're done, right? Because we just want at least one of these independent events. And then the other chance, 3/4 is if A does not occur. And then if A does not occur, we still look for if B occurs. So then we multiply this by the chance that B will occur, right? So this is 1/4 of if A automatically occurs, we're successful. And then this part is if A is not immediately successful, so the 3/4 chance, then we look at the probability that B will occur, which is 3/8. In this scenario will also be successful, right? So that's why we add this part. So now our total probability will just be the sum, which is just 1/4 plus 9/32, which is just 17 over 32. And that's our answer. The probability, or sorry, the population of Expo Town is currently 54,000 people. If the population has increased by 200% in the past 30 years, what was the population 30 years ago? Okay, so basically, we just have X, the population that was 30 years ago, and it was increased by 200%, right? And if you have it increased by 200%, you're multiplying it by 1 plus 200%, which is 1 plus 2, right? So like you can think of if you're increasing something by 100%, that's doubling it, right? And that's because you have 1 plus 1. You have X times 1 plus 1. And if you're increasing it by 0%, then you're just multiplying by 1 plus 0, which is just 1. So you're keeping it the same if you're increasing by 0%, right? That makes sense. So if you're increasing this by 200%, you're multiplying this X by 3, right? So if we're just multiplying this by 3, we're getting 54,000 people, and we want to find what our original amount was. We just divide 54,000 by 3. So then this is just 18,000. And that's our answer. if a plus 2b plus 3c equals 30 and a plus 3b plus 5c equals 8, what is the value of a plus b plus c? Okay, there are a few ways you can do this. One way, because you're given three variables but only two linear equations for them, you're gonna have like infinite solutions. So basically, you can assume any one of these variables to be a certain number, and then solve for the other two variables, and then just sum all of your three variables together. You can do this because um, you're gonna have infinite solutions on this because you have more variables than you have equations. Another way you can do this is there's a bit of a clever way to like add these equations together. You can take the a plus 3b plus 5c equation equals 8, and you can subtract it by this other equation, and then you have b plus 2c equals negative 22. And then what you can do is you can subtract this from a plus 2b plus 3c. And then this will be a plus b plus c, and this equals 52. So then that's just your answer. This is probably the best way to do it, but the other way to do it of assuming one of these variables is something, that's also a fine way of doing it. That also wouldn't take you too long. But yeah, the answer is 52. Anything you want to say on that, Bill?
Yeah, probably just solving for A, B, and C. I don't think that will be a good idea because just the fact that, two equations, three variables. So, yeah, I don't really know what to say about this.
Or I feel like, I don't know. Unless you can see this very easily, I feel like it would almost be better just to go with the solving method because,
But would you be able to solve it though?
yeah, you can just assume any one of these variables is something, and then you can solve for the other two variables, and then you just add all of them together.
Okay. Oh yeah, that makes sense because yeah, if you assume one of them to be a 0, then because the other two are only related to that one, that's like a relation, not an exact number. Yeah, that makes sense. Okay.
Yeah, I was saying like on the test that might be better because like it's going to work and you just go through with it. And if you're looking for something special like this, it might take you a while to find it. So I know. But I guess it's your choice.
Yeah, it's just up to if you notice something like that or not.
Okay, a bag contains 10 identical blue marbles and 10 identical green marbles. In how many distinguishable ways can 5 of these marbles be put in a row if there are at least 2 blue marbles in the row and every blue marble is next to at least one other blue marble? Okay, I'm not sure what this picture is right here. I'm not sure if it was like colored in the original or something. But it's fine. We don't need a picture for this. Okay, so basically we have 5 marbles in a row, and we need at least two blue marbles in the row, and the blue marbles have to be next to at least one other blue marble. I'm not sure why it gives us like the bag contains 10 identical blue and 10 identical green. Again, that's unnecessary. We just want to find how many ways this can occur. Um, I think the best way to do this would be casework and how many blue marbles you have in the row. There could be other ways you can do it, but I feel like casework is a pretty fast way, and it's also like, when you see the problem, you can just think of, oh, casework, I can do this by casework, and you can just go through with casework. Okay, so if we're doing casework, and we have at least 2 blue marbles in a row, we're going to need to do casework of 2 blue, 3 blue, 4 blue, and 5 blue. If we have 2 blue marbles, then we just think of where these 2 blue marbles can be in the row. Now they have to be together, right? So then there's only going to be 4 places that we can have the 2 blue marbles in, right? We can either have it both at the start, so like blue at the start and the rest are green, or you can have 1 green and then the 2 blue marbles, or you can have 2 greens and then the 2 blue marbles, or you can have 3 greens then the 2 blue marbles. So that's 4 cases. And this is just 4 cases, right? Because it only matters on where the positioning of our blue marbles are, because the rest are going to be green no matter what, and you can't like arrange that in any more ways. So then our 2 blue marble case just has 4 ways. Okay, now 3 blue marbles. So it's just going to be like the same thing as 2 blue marbles. All the blue marbles have to be together, right? Because if you have 2 blue marbles that are together and the other one was not, that's not going to work, right? Because the other one has to be with at least 1 other blue marble, right? So all 3 blue marbles have to be together. And then we just find how many ways you can position that, which is just going to be 3 ways, right? So like, you can have them all at the start, in the middle, or all at the end. So that's 3 ways. Now the 4 blue marbles, you can have them either all together, and then that would give you 2 ways, either at the start and then 1 green marble, or 1 green marble and at the end. But you can also have them like separated, right? You can have them as 2 blue here, and then a green in the middle, and then 2 blue at the end. This works because the blue marbles are still paired, sorry, and there are 4 blue marbles. And this is the only way you can have them separated and still work, right? Because I don't know, for them to be separated, you have to have a green marble in between, and then this is the only way you can do it. So then our 4 blue marble case is going to have 2 plus 1 ways, so 3 ways. And then our 5 blue marble case, that's just a trivial 1 case. They're all blue, so that's just 1 case. And then you just add all this up. Then that's 11 cases. And that should be our answer. Anything you want to say there, Bo?
Not really. This is just casework. I don't really see it any other way you can do this.
Yeah. Okay, for how many integers n in the set 1, 2 to 20 is the tens digit of n squared odd? Okay, now for this one, I think the best way for you to do this question is just to list out all of the first 20 integer squares and then find which of those have a tens digit that is odd. The only other way I can really see you doing this is with some weird modulus way. Like, I don't even know. Like, just there's something weird with modulus, but that would probably take a while to think of, right? And if you just list out the first 20 integer squares, that shouldn't take too long, right? You should have your integer squares remembered to at least up to 20. If you don't, you should memorize them. So then you just list out 20 numbers that you already have memorized. That should not take too long. Again, I can only really see something else working with modulus, but that would take a while to think of, and you just want to do this as quick as possible. So yeah, I think the best way would just be to list them all out. So let me just do that. You can see how long I take on this. So there's 1, 4, 9, 16, 25, 36, 49. So we're on 8, 64, 81, 100. And then we go to 11, 121, 144, 169, 196, 225, and then 16, 256, 17 is 289, 18 is 324, 19 is 361, and then 20 is 100. So how long did that take me? Like maybe 20 to 30 seconds. So really not that bad. And now we just look at which of these have odd 10 digit. We have one here on 16. We have one here on 36. These are all even, even. And then this one is 5 odd. Even. Wait. Oh, no. This one is odd. My bad. The 9 is odd. Okay. And then all the rest are even. So then we just have 4 integers that work. And that should be your answer. Yep. Anything you want to say on that, Bill?
Memorize your memorize your squares, I guess.
Yeah.
Memorize your squares. Those are useful. If you don't have them memorized, a cool trick is say you have say you don't know what 19 squared is. You can take 20 squared and then minus 20 and then minus 19 to get 19 squared.
Yeah.
That works for like all squares. So a minus 1 squared plus a minus 1 plus a equals a squared.
Yeah.
Okay.
Okay, but I was gonna say you should have all your squares memorized to at least up to 20. I don't know. It's only 20 numbers, so it, so it's not that bad, and it's pretty useful. So I would say at least get to memorizing the first 20. And I would say if you can, you want to try to memorize more. I'd say up to 30 for that is probably good. Um, those extra squares can probably help you in a lot of stuff. And if you're doing UIL number sense, memorizing squares is like even more crucial, right? Because you got to go fast, and a lot of arithmetic that you can do, it might just have like some square or something, right? So for number sense, I would probably say memorize like as high as you can. Maybe up to 50 for number sense would be good. But yeah. Okay. Next question. Line L containing the points -11, 4, or -11, -4 has the same y-intercept as y equals -3x minus 2. What is the product of the slope and y-intercept of line L? Express your answer as a common fraction. Okay, so we know this line contains the point -11, comma -4. Has the same y-intercept as y equals -3x minus 2. Well, this y-intercept is just -2. So then we know that this also has a y-intercept of -2. If it has a y-intercept of -2, then we know it contains the point 0, comma -2. So then we can find its slope from this by just doing algebra 1 stuff, right? -4 plus 2 over -11. So then this is 2 11s. So line L's slope is 2 11s. And we know its y-intercept is -2. Want to find the product of these two numbers, then it's -4 over 11. That's your answer. This is a pretty straightforward question. You just do it exactly like this. Okay. Triangle ABC is a right triangle with AB equals 8 units, BC equals 10 units, and AC equals 6 units. So 6, 8, 10 triangle, that's a right triangle. But it also already gives you the right angle. So yeah. Okay. Triangles BDC, AFB, and CEA are isosceles with vertex angles of 90, 120, and 120 respectively. If R denotes the area of CEA, and S denotes the area of AFB, and T denotes the area of BDC, what is the value of R plus S over T? Express your answer as a common fraction in simplest vertical form. Okay, so area of CEA is R, area of AFB is S, and area of what? And area of BDC is T. So you want to find this triangle area plus this triangle area over this triangle area. Now, there are multiple ways you can find the area. One way you can do it is so like looking at triangle CEA, right? We know that this is 120 degrees. We know that its sides are isosceles, or I mean the triangle is isosceles, and the sides are the same. And we know that this side, the base side, is going to be 6 units. It's given on all the base sides. Okay, and we want to find the area of this triangle, right? There are multiple ways you can do this. One way is to drop this altitude, and because it's isosceles, this will also be the midpoint of the side. So then each of these are 3, just taking 1/2 of 6, right? And then because this is isosceles, this altitude is also the angle bisector. So then these angles in these smaller triangles are 60 degrees, and this is the altitude, right? So then this is 90 degrees, and then this is 30 degrees. So now we have a 30, 60, 90. So then from this, we can just calculate the height right here, right? So this is on the 60 side, and this is on the 30 side. So then this height is just going to be 3 over root 3, right? So then the area of this triangle, we have this height, we have this base. That's just going to be 1/2 times 3 root 3 times 6. And there are a lot more ways you can find the area of a triangle. You can also find this side, which would be like 6 root 3, and this side will also be 6 root 3, and then use the 1/2 AB sine theta, and we know that the sine, we know the measure of this angle, and it's a special angle to where we can find the sine of it. So then we can use 1/2 AB sine theta on here, right? So then another way finding the area would be doing 1/2 times AB. AB would be 6 root 3 on both these. So then it would be 6 over root 3 squared times the sine of our angle in between, which is 120. Do either way. There are probably other ways to find the area as well. But yeah, just find a way to find the area and use that. Okay, so just taking the top expression, we're going to have 1/2 times 18 over root 3, which is 9 over root 3. We probably want to rationalize this, but honestly, it's not too important until you get to the end. So like right now, you could just leave this as 9 over root 3, or you can rationalize it if you want to. If you rationalize it, you're going to get 3 times root 3. But you can just keep it as 9 over root 3 if you want to. It doesn't really matter. Okay, we want to do the same process to the other 2 triangles. So now let's look at AFB. Now this one is pretty much the same as the one we just looked at. It has a vertex angle of 120 degrees. We know its base side is 8. So you just do the same thing, but it's scaled. So this side is going to be 4. We know that this is 30, 60, 90. So that means this side is going to be 4 over root 3. So then the area of this triangle is going to be 1/2 times 4 over root 3 times 8. This is then 16 over root 3. You can rationalize this if you want to. Then it's 16/3 times root 3. Okay, last triangle. DCB. A little bit different from the other triangle since this is a 90-degree angle. And we know that this side is 10. Okay, but this is still fine. We can use the same tactic of dropping this altitude. So we drop this altitude, it's 90 degrees here, and because this is an isosceles triangle, it's also going to be the angle bisector. So then we're going to have this as 45 degrees, and then we have a 45, 45, 90 triangle. And again, this is also going to be the midpoint of this side, right? So then this length right here is just going to be 5. So that means our height here is just going to be 5. So that means the area of this triangle is just going to be 1/2 times 5 times 10. which is just 25. Okay, and if you look at the RST stuff again, you're gonna see that we want to find the area of this plus the area of this over the area of this. So then just combine all those numbers. We're gonna have 3 root 3 plus 16 thirds root 3 over 25. This is going to be 9 thirds root 3. So add that to 16. That's going to be 25 thirds root 3 over 25. And then we get 25 on top and bottom. So then this is just 1/3 times root 3 or root 3 over 3. And then this should be our answer. Yeah, that's our answer. A bit of a long problem, but it's still manageable.
Right.
Yeah. What?
So
do you want to say something?
yeah. It is possible to do this problem without having to find the exact areas, because say for triangle CA and ABF, right? For those triangles, you can find out like what the ratio of their area is. So we could just say that we can represent like S in terms of R, and then similarly for CDB, it might be a bit harder, but it wouldn't be impossible. We could find the ratio of two triangles with the same base, but two isosceles triangles with the same like base, but one of them is 90, one of them is 120. Find the ratio of that, and then using the ratio of that, we can also multiply that by the ratio um of the side length to get the ratio. So that way we can represent CDB in terms of R also. So that way we don't have to like find out the area of each one of them.
Um, I feel like, yeah, you can do the scaling on the two isosceles triangle with 120 degrees. I mean, because that's fine. Like, you just directly do that.
Mhm.
Uh, from the 120 to the 90, I don't know. I feel like deriving that would just kind of take long. And like, if you just find the area of the 90-degree one, I feel like that wouldn't take as long, and it's also straightforward. Um, but
Right.
it, yeah. I mean, your way is also probably valid, and you can also do it if you
Yeah,
want to.
just deriving you can first of all find just like ratio of area between like a 120 and a 90 that have the same side length, and then like find the ratio of their side length, and then you can multiply those two together. I
Sure.
feel like that wouldn't be too difficult. That's how I did this problem. So
Okay.
yeah.
I mean, yeah, sure. You can do it like that if you want to. I just feel like just getting the area of the 90 would be more straightforward, but it's your choice. Okay. Um, but is this the answer? Yes. Okay. In the figure, a circle is located inside a trapezoid with two right angles so that a point of tangency of the circle is the midpoint of the side perpendicular to the two bases. So this point of tangency right here, E, is the midpoint of this side. The circle also has points of tangency on each base of the trapezoid, so here and here. The diameter of the circle is 2/3 the length of segment EF, as shown. If the area of the circle is 9 pi units squared, what is the area of the trapezoid? So for this, we can just find the length of EF and find the length of this height thing. Because the area of a trapezoid is just going to be this average length of the bases, which is EF, times the height between the bases. So yeah, we can just find those two lengths, and that should be pretty easy, right? Because we're given the area of the circle, we can find the diameter from this, and then we're given EF is like 2/3 of the diameter, and this length right here is just the diameter, right? So then we can just do it like that. and EF is gonna be the average of these two bases because this E point right here is the midpoint of this side, right? Okay, so then let's find what the diameter of the circle is. If the area is 9 pi, then the radius is going to be 3, right? Just divide that by pi and square root it. And then our diameter from this is going to be 6. Now, if this is 2/3 the length of the segment EF, then EF is going to be length 9. And then this height right here, this is just the diameter of the circle. So then it's just 6. And then area of the trapezoid is going to be this times this, which is just 3/4. And that's our answer. Anything you want to say there, Bill?
This problem is pretty straightforward. I don't think there's really anything to say.
All right. The sum of the reciprocals of 3 consecutive positive integers is equal to 47 divided by the product of the integers. What is the smallest of the 3 integers? Okay, so let's just label the integers as something. Let's just label them as A, B, and C for now. Now, I know they're consecutive, and we should use that in the future. I'm just gonna say they're A, B, C for now. Okay. Now we're told that the sum of the reciprocals of these, so 1 over A plus 1 over B plus 1 over C, is equal to 47 divided by the product of these integers. Now this is not a great expression to work with. Just directly, like right here, you really don't enjoy like having 1 over the reciprocal of positive integers. So we want to try to manipulate this expression to see if we can find anything that's better. One thing that you can think of doing is adding all this side together and making it into a big fraction. And then if you do that, the denominator will be ABC. And then you can cancel that with the denominator of ABC on this side. So, if we do that, we're going to have AB plus BC plus AC over ABC. It's equal to 47 over ABC. And then we can cancel out these two denominators. Then we have AB plus BC plus AC. And this is easier to work with. We don't have reciprocal positive integers anymore. And okay, we know that these are 3 consecutive positive integers. So you can solve this with now substituting, A as x, B as x plus 1, C as x plus 2, and solving for x in a quadratic. That's not bad. You can also do that. But one thing to notice is that this 47 number is really low, right? Like our integers are gonna have to be really small, right? Like if we do 5, 6, 7, the product of these two integers is already 30. So there's absolutely no way that we can have 5, 6, 7 as these 3 consecutive integers, and it's gonna have to be much lower. And we know they're 3 consecutive positive integers, so we really don't have very many cases here. So I think a better way to do this would just be testing 3 consecutive positive integers and finding which have the sum to 47. And again, there's like very little cases to try here, so really it's not going to take long at all to find which 3 work. So let's just say we try 2, 3, 4 first. We can see that this is 6, 12, and then 8. If we add this is 26. Not enough. So let's try to go one step up. 3, 4, 5. This is going to be 12. This is going to be 20. This is going to be 15. Then we have 27 plus 20, which is 47. There we go, we got it. So that was very fast. I think it would be much faster than trying to solve the quadratic, expanding the three terms out and then solving the quadratic. I think that would take a bit longer. Okay, so then from here, we just know that our three integers are 3, 4, 5. The smallest is 3, so then our answer is just 3. Anything you want to say there, Bill?
Mm, I mean, I think this like requires like a feel for the numbers. Like you just feel like, yeah, 345 is probably what it's gonna be. Um, yeah, I don't really have anything to say here.
Okay. Okay. The first three terms of a geometric sequence are 3, 6 plus p, and 30 minus p, and each term is a positive number. What is the fifth term of the sequence? Okay, we know that it's a geometric sequence, and we want to utilize that. Um, so the algebraic way of solving this would be to say the ratio of 6 plus p to 3 would be equal to the ratio of 30 minus p over 6 plus p. And from here, you can solve for p. And then you can get the geometric sequence. So yeah, you can do it like this. If you can also just it tells us that each term is a positive number. So it's probably going to be like a really nice ratio, like just some, or no, oh, it's a positive number, not an integer. Never mind. So, I guess it might be a bit better to solve it algebraically. I was saying like if you can just from here like tell what p is and find something that works, you can go with that. Or you can just solve it algebraically and just find p like no matter what. But yeah, your choice on that, I guess. Okay, so solve this. We just cross multiply. We're gonna have 36 plus 12p plus p squared, and this is equal to 90 minus 3p. So we're gonna have a quadratic in p squared plus 15p, and then it's gonna be minus 54. Okay, we solve this quadratic. Try to find factors. Or we can use quadratic formula, but these numbers are kind of big. The correct factors are going to be p plus 18 times p minus 3. So this multiplies to negative 54, and it sums to positive 15. And then because the terms have to be positive numbers, p will have to be 3, right? If p was negative 18, then 6 plus p, negative 18, would not be a positive integer, or a positive number, sorry. So then p would have to be 3, and then we can see that our sequence was 3, 9, 27. So then our ratio is 3. So then we can just multiply this to get to the fifth term, sorry. So our fourth term is going to be 27 times 3, which is 81, and then our fifth term is going to be 3 times 81, which is 243. See, that's our answer. Anything you want to say there, Bill?
No.
Okay. Standard die whose faces are number 1, 2, 3, 4, 5, 6 is rolled 3 times. What is the probability that the sum of the numbers rolled is 8? Express your answer as common fraction. Okay, this one, I would say the best way would be to do this with casework. There's not that many cases, and it's not that bad to do with casework. There could be other ways you can do this, but I mean, it's probably more complicated, like some weird, I don't know, stars and bars stuff. But it's really not stars and bars because your die can only be 1 through 6, and it can't be all the way to 8, right? I don't know. Is there a modified stars and bars, Bill? Or like, there's a
Modified?
maximum?
Um, uh, I've never heard of a modified stars and bars.
Okay. But yeah, I think it would be pretty weird if you were doing some other way than casework. Um, so I just say do casework, and when you see this problem, you can just immediately think of casework, and you can just go through with casework, right? So it's also good in that you can see it immediately, and you can just like go through with it to find the answer. Okay, so if we're doing casework, we want to find the combinations um, of die rolls that we can get to have the sum of those numbers to be 8. And there's not going to be too many combinations for this. Let's just think of let's think of combinations that will need 1 first. So if we have 1, then our 2 other numbers has to sum to 7. And then we just think of all the ways 2 die rolls can sum to 7, which you can just listen down, right? It's gonna be 1, then 2, 5, and then 3, 4, and that's all you're gonna have. So these are the ways you can sum to 8 if we have one of the die being 1. So now let's look at one of the die being 2. Then the rest have to sum to 6. One way we can do that is 3, 3. Another way we can do that is 2, 4. Now we could do that with 1, 5, but we listed already all of our cases with a die rolling 1 right here, right? And so we don't want any more cases that have a 1 in them, because then they would be repeating someone in here, right? And we can see that's what's happening. 215 is a repeat of 125, and we don't want that to happen. We're gonna put in the arrangements of these later, but we first want to just list out the original or the unique. We just want to list out the unique combinations of die rolls first, and it's also better in that regard because you can see which ones have all 3 numbers unique and which ones have like repeatings, and then you can factor that into how many arrangements they have. But anyway, so this is going to be all of our combinations for the dice with 2, and then if we try 3, there's not going to be any more, right? Because we're going to need at least one die with 2 or like a die with 1. That's not going to work, right? Because we've already listed down the cases where we need 2 or 1. Okay, so then we only have 5 unique cases, which is all of these. And now we need to factor in arrangements, right? So 116, it has a repeat of 1. So that means there's only going to be 3 ways to arrange this. 125, these are all unique. So that means there are going to be 6 ways to arrange this. So we just look at all of them like this. This is going to be 6, this is going to be 3, and this is going to be 3. Now we look at the probabilities for each of these arrangements. But each of the arrangements are always going to be 1 over 6 cubed no matter what, right? Because each of the dice are independent probabilities, and you always have equal probabilities, which is 1/6, to roll any one of these numbers, right? So it should be pretty easy to see that if you're given any one arrangement, you will always have a probability of 1 over 6 cubed to get that certain arrangement. So then we just multiply all of this by 1 over 6 cubed. So multiply this by 1 over 6 cubed, multiply this by 1 over 6 cubed, and do that for all of this. But an easier way to do this would just be to sum all this first and then multiply by 1 over 6 cubed. So then if we do that, we'll get 21. Now we multiply this by 1 over 6 cubed. So then we have 21 over 6 cubed. And then we can take out a 3 from 6 cubed, and then we have 3 times 2 times 6 squared. And then cancel this with 3 from 21. So then we have 7. So then we have 7 times 2 times 36, which is the bottom is what 36 times 2, which is 72. Like, what? Okay, no, okay. Okay, so then our answer is 7 over 72, and that's correct. Anything you want to say there, Paul?
Yeah, normally when you have like a problem that's asking like sum of like dies that sum to a certain number, you normally I think it's normally like you want to do casework. It's kind of hard not to do casework on a problem like this. I feel like on like a problem like this. Is there any other way to do this
Yeah.
besides casework, do you think?
Or if the sum is less than 6, you can do stars and bars, right?
Stars and sum is less than 6?
Like 6 or
Oh
less.
yeah, no, I guess you could do stars and bars if it's 6 or less.
Yeah. Would that be slightly faster, I guess?
Ooh, it it probably would be, but that's kind of like
I
a
guess.
very niche case, I would
Well, this
say.
like casework is like fine to
Yeah,
use.
casework is fine. If you have dies that are adding up to something, that's normally just going to be casework.
Yeah. Um, well, I also realize if you have a problem and it's something like you're summing like groups and you're summing it to a constant number, and maybe it's something like weirder that's not like dice rolls, so then you don't really want to use casework. You want to recognize that as probably stars and bars. So you know you just want to have stars and bars in your toolkit also. So like yeah, like learn stars and bars if you don't know stars and bars yet. It's useful sometimes. I'm not sure how much. Or we saw one math counts problem before that used stars and bars, right? Like it was a train problem.
Yeah, it was the train problem where we had to use stars and bars.
Yeah, stars and bars is also useful. So also learn it if you do not know it yet. Um, yeah. And by the way, like a bunch of these various math techniques, like I don't know, uh, stars and bars, and I don't know, like triangle properties and like stuff. Like a bunch of this stuff is in the art of problem solving, volume 1 and volume 2 books, and generally those are like very useful for competition math, especially like AMC and math counts and like this sort of region. Um, so basically, you should check out like art of problem solving volume 1 and volume 2 books and like read them in really good detail. If you want to be like uh, good at competition math, I guess. There's a lot of useful stuff in there. Uh, Anything you want to say about that, Bill?
Yeah, either that or just like look at a lot of problems on our problem solving. Like just look at them. Like just look at the descriptions
No,
and like
I feel like the volume 1 and volume 2 books are like really useful though. Like
yeah,
um
probably. I've never used them, probably, but I think
oh
they're.
really?
I've never used them.
They have a bunch of techniques. Um and they have like chapters divided based on like I don't know geometry or number theory and stuff. And they also give like a bunch of problems for those sections. So like you know you're working in number theory, and it will give you a bunch of problems specific to that chapter, specific to that subject. Um,
Yeah,
all,
I think I just like I did enough problems that like I flipped through them once. I have the books. I've never used them. I just never used them. I
but
think
you have the books, but you never
I
use
have the
them.
books, but I never used them. Yeah, like when I
Hmm.
finally got around to using them, I realized like I pretty much have figured out all the techniques in there. It wasn't really any point to me. I just did a lot of
Okay.
problems, so. But yeah, if you don't know like a lot of techniques, those are definitely a good place to look. Just going through them.
Yeah. Um, also, I don't know if money is an issue.
You could always
You can
pirate them.
also, yeah, you can always pirate them. Uh,
Yeah.
don't tell anyone I said that. I don't know, but yeah, you can pirate them on like
Uh,
websites like LibGen.
yeah,
But
LibGen.
yeah,
Just Google LibGen or Library Genesis. You can pirate those books.
yeah, no, you can get a bunch of stuff on LibGen.
Yeah,
Like,
pretty much
oh,
anything you can get on LibGen.
yeah, almost anything. Like
Like any
anything
book.
that's not too recent or not too old, probably.
Yeah.
Um, or do they just do academic books, or do they also do like I don't know
No,
novels
no,
and stuff?
there's novels on there. I pirated novels from there.
Oh wow, okay. So yeah, Legion. Yeah, you can get a lot
I
of stuff on
pirated
there.
fairly modern novels from there too. So
Modern novels.
yeah, like pretty
Okay,
modern ones.
okay, yeah. Wait, do they have a focus on academic stuff though? Or, I don't know.
I'm not sure. I'm not sure.
Okay, but yeah, check out LibGen if you want to get some stuff for free. Okay. Um. Okay, let's continue with our problems. So we're on number 18. If x, y, and z satisfy xy equals 1, yz equals 2, and xz equals 3, what is the value of x squared plus y squared plus z squared? Express your answers as a common fraction. Okay, when you see this, xy equals something, yz equals something, xz equals something, um, you should immediately recognize this as like how to solve for x, y, and z in this case. Um, like I don't know, this comes up a fair good amount, and you should just always know like if you see these three things, you should always know how to solve them, I guess. So what you do is you multiply all three of these terms together. So if you do that, you're gonna get x squared times y squared times z squared equals 6. And then you can square root both sides so that you get x, y, z equals root 6. And then from each of these equations, so like xy equals 1, you could divide this from xyz equals root 6, and then you will get what the missing variable here is, right? So, you can take xyz over xy. This will be equal to root 6 over 1. And then from here, we see that z will equal root 6. So then you can do this for all of them, and you will get what each of the individual variables are, right? So here x will equal root 6 over 2. Here y will equal root 6 over 3. So so yeah, just recognize if you have all three of these, if you have what xy is, yz is, and xz is, you can use this technique to solve for each of the variables. Yeah. Okay, and then once we found the values of these variables, then we can just plug it in onto this expression and get its value, right? So then x squared is just 6 over 4, y is just 6 over 9, z is just 6. So then this is just 3 halves. This is just 2/3. This 6. Then this is 9 plus 4 over 6 plus 6, which is 13. 6 plus 6, which is 49. 6. That's our answer. Anything you want to say there, Bill?
Right. When you have something like this, like if you have like X, Y, and Z, and like in the problem like it gives you like X, Y, Y, Z, and X, Z. It doesn't matter if you're like multiplying or adding. There's probably a way for them to combine them, for you to combine them, and then take those out and like find individual X, Y, and Z. So like if it's like X plus Y, and then you have Y plus Z, and then X plus Z, you can add all three of them, and then subtract them individually. And then in this case, you're multiplying them.
Yeah. All right. Um, let's move on. A cubicle room has edge length 10 feet with A and B denoting two corners that are farthest apart. A caterpillar crawls from A to B along the walls. In feet, what is the length of the shortest path from A to B that the caterpillar may have taken? Express your answer in simplest radical form. Okay. Um, so we have a cubicle room, and A is here and B is here. And the side lengths are 10 feet. And a caterpillar crawls only on the walls, right? So only on these sides. And, it crawls like in some path and then it gets to B. You want to find what the shortest path that it can take is. Um, it, it should be, I don't know. It should be pretty obvious that the shortest path would have to be like A to the midpoint of the side, and then the midpoint of the side to B. Um, or I don't know.
Okay, so a way you can think about it, this is that if it's crawling to the other one, it will go through two faces, right? So you can like fold out the other face so that you end up with just one rectangle that's 10 by 20. Does that make sense? And then you just connect A and B.
Okay, yeah, yeah. You can think of it. Okay, yeah. That's actually really good. So, okay, it should be pretty obvious that the caterpillar has to crawl on just two faces, right? I mean, if you're going three or more faces, I don't know what you're doing, man. I mean, then you're going some weird path, and that's going to be like way too long, right? Um, so then if you're just crawling on two faces, then you can expand um these two faces into a rectangle like this, right? And it's two squares. And then you have A and B here, right? So then it's a very obvious that the shortest path would just be this straight line. And then this would intersect this side at the midpoint. Okay, and then we just want to find this. We can even use this figure to find what the length is. This is going to be 20, this is going to be 10. So then it's just going to be Pythagorean theorem rooted, and this is just 10 root 5. And that's going to be our answer. You can also just do this as two right triangles on this cube right here. So this is going to be 5. So Pythagorean theorem on this would be, 125 rooted, which would be 5 root 5. So this is 5 root 5, and this is symmetrical. So this is also going to be 5 root 5. So this whole length is also going to be 10 root 5 by doing this way. So you can also do it like that. Okay. Yeah, let's move on. What is the maximum value of xy if x plus 1 over y equals 7 halves and y plus 1 over x equals 7 fifths? Express your answer as a decimal to the nearest 10. Okay. For this one, so one way to solve it would be to multiply these two expressions together. So multiply x plus 1 over y by y plus 1 over x equals 49 tenths. And why this works is because like these terms 1 over y times y and x times 1 over x, these are going to cancel out, while the terms that don't cancel out, so 1 over y times 1 over x and x times y, those are going to be terms with x, y in them. So multiplying these two together is going to be is going to give us a really good expression to work with. And I'm not sure, like, there's another really good way to solve this. Like, if you, from the first equation, if you say x is 7/2 minus 1 over y, and then you substitute this into the second equation, so like y plus 1 over 7/2 minus 1 over y equals 7/5. And this is like a really messy equation, right? And I don't know. So I think for this one, you just have to kind of notice that if you multiply these two expressions together, you're going to get a really good expression that are going to have two terms with x, y in them. I don't know. Anything you want to say on that, Bill?
No.
Okay. Yeah, I guess it's just noticing that. I don't really see any other great way to do this. Okay. But yeah, if you do multiply these two together, you'll get 1 plus 1 plus xy plus 1 over xy equals 49/10. And then there's 2 on the side, you can subtract it. Then you'll have xy plus 1 over xy equals 29/10. And it's pretty good. You have an expression in xy, right? And this is just going to be a quadratic equation, right? You can just multiply both sides by xy. So then we have xy squared plus 1 minus 29/10 xy equals 0. So then we can just solve this with a quadratic equation. So we're going to have xy equals -1 plus or minus 29/10 minus 4. Oh, whoops. 29/10 squared minus 4. Oh, whoops. This should not be -1. This should be, okay, my bad. This should be plus 29/10. And then it's going to be over just 2. Okay, so let's try to solve this. So 29/10. Okay, so 29 squared, I mean, that's not bad. You can just multiply that out. But again, having squares memorized up to like 30 is pretty useful. So if you have this memorized, that would be good. It saves you a few seconds. Another way you can do it that might be slightly faster than just multiplying this out would be knowing that 30 squared is 900, and then 29 squared is going to be 30. It's going to be this minus 30 minus 29. So this minus 59, which is just going to be 841. Okay, but in any case, this square is just going to equal 841 over 100. And then if we're subtracting this by 4, this is going to equal 441 over 100. And then 441 is 21 squared, right? So then we could take this out of the radical as 21/10. So then we have 29/10 plus or minus 21/10 over 2. And this is equal to xy. Okay, and we want the maximum value of xy. So you want to take the positive value here to get the maximum. Then we have 50/10, which is equal to 5 over 2, which is 5 has. I mean, like, we have 50/10 over 2, which is 5 over 2. I don't know why I wrote 5 over 2 again, which is 2.5. It says decimal to the nearest tenth. It is 2.5. There you go. That's our answer. Also, by the way, seems like every time it asks like express your answer as a decimal to the nearest tenth, like every time it says that, like you always have to utilize the nearest 10, like the 10th that 10th place. Like basically, if you see a math counts question and it says put your answer as a decimal to the nearest tenth, and you got like an integer answer, I think you should check your work because like of all the problems we've worked on so far, I feel like it's always been the case where you need to use that 10th place. Um, but yeah, um,
And even if like you don't need it, you should put like dot zero. You should
oh
put
yeah,
dot
put
zero.
down zero. But like if you get an exact integer answer, I think you should check your work. If you get like a long decimal, I mean, this should be pretty uncommon though. If you get like a long decimal, 2.0345, and it asks for the nearest tenth, I guess you can go with 2.0. Um, but in this case, I still feel like I don't know. Okay, I guess this is fine. But if you get an exact integer answer and it says like tenths or hundredths or anything, I think you should check your work because I've never seen a question where it asked that and the answer was an integer answer. So I feel like that's just a good tip for math counts. Um, for any other competition, it might be different, but this is just from my experience with doing a lot of math counts problems. Okay, I need to find some space here. Here's some good space. Number 21. A sphere's radius 4 inches is inscribed in a cone with a base of radius 6 inches. In inches, what is the height of the cone? Express your answer as a decimal to the nearest tenth. Okay, we have a sphere and a cone. The sphere is radius 4 inches, and the cone has a base of radius 6 inches. Um, and we want to find what the height of the cone is. Woohoo, 3D geometry. I love 3D geometry. Okay. Okay, so really I can only see like one way to do this. I don't know. I what do you think, Bill?
Well,
Just one way?
what is your one way? You should tell me what your one way is, and then I can say if my way is different than yours.
Wait, what? Wait,
You
did I not did we not talk about it before?
you talked about it. I didn't quite follow you fully.
Oh, wait, what is your way?
Take a cutout and then. Oh wait, mine was trigonometry, so yours is probably different.
Trigonometry?
Yeah,
What?
yeah. I remember yours not being trigonometry, so.
Wait, how do you use trigonometry?
Oh, so the bottom, like, you can make triangles, right? If you do like a cutout. Uh,
Like a middle cutout?
yeah, and yeah, like a middle cutout. You make a triangle, and then the bottom you can make 3, 4, 5 degree. You can make 3, 4, 5 triangles on the bottom, right?
Uh, 3, 4, 5 triangles at the bottom?
Yeah.
Wait, how?
Hang on, I'm just gonna share my screen. Hang on.
Then I had to unshare for you to share.
Uh, yeah, I think you might have to unshare it. Let me share. Okay. Okay. So, like, you have it like this. Kind of looks like this. Yeah. There we go. This, and then like here's a sphere, right? So if this is like the middle of the sphere, oh my goodness, this will be 4. This will be 4. This will be 4. right angle, right angle, right angle. If you connect it like this is 3, right? Wait, this isn't 3. Hang on. Oh, this was 6. Oh, never mind. Then I messed up doing
Nice.
I messed up doing this then. Never mind. Okay.
Uh,
I mean, it's probably still possible because you could figure out if you connect this like this, you can figure out what this length is, right? 4 6. That's 2 3.
how would that length help you though?
If you find this, the you can find cosine and sine in this angle and cosine and sine in this angle because this is 3 2. This is 6 also, right? You can find cosine and sine in this angle and cosine and sine in this angle. So now you can
Wait,
find
how's that also 6?
what? A
Uh,
circle, tangent circles, right? These are tangent circles. These are both tangent, so they they meet at
okay,
this point
sure.
from there to there, there to there.
It's just like congruent triangles.
Yeah, yeah. These are congruent. So we can find the cosine and sine of these two angles. And then from that we can find the cosine of this angle. So we have 4 here. And then so we can find this length.
Like do 90 minus those angles or something?
180.
Or I mean 180, yeah.
Yeah, yep. That's
Oh,
how I do it.
okay. That could work. I feel like mine is a little bit better. I don't know.
Okay.
Um, Here, I will show my solution. Okay, here's my solution. Um, it is also we're also going to use a middle cutout of the cone. So we got a circle here, and then let's draw this whole height. Okay, I should probably draw my circle better. Oh my God, I can't draw a circle. Like I can't draw a circle. Oh my God. Okay, so let's drop this height down. We're taking the middle cut section. Okay, so this is going to be 6. The radius of the circle is going to be 4. This is the center. This drop down is going to be 4. Okay, so this whole thing is our height. And this here is going to be our height minus 4. This is going to be a right triangle right here. This is tangent to this side and stuff. So that's going to be a right angle. And this big triangle, so here, down here to here, that's also going to be a right triangle. And I can see that this smaller right triangle here is going to be similar to this larger right triangle, right? Since they share the same angle and they share a right angle, right? So then we can use 4 over 6 is equal to h minus 4 over this hypotenuse length. And what is this hypotenuse length? Well, it's gonna be h. This whole thing is h, right? This hypotenuse length is gonna be the root of h squared plus 36. So then we have this equation, 46 is equal to h minus 4 over h squared plus 36. And this is going to be equal to 2/3. So then we can expand this out, cross multiply. Then we have 2 times root h squared plus 36 is equal to 3h minus 12. Or, we could just say root of h squared plus 36 is equal to 3/2 h minus 6. And now we can square both sides and we will have a quadratic in h. H squared plus 36 is equal to 9/4 h squared minus what? Minus 18h plus 36. And the 36 cancel, which is the really nice part. And then you have 5/4 h squared minus 18h is equal to 0. Then h times 5/4 h minus 18 is equal to 0. Because we are assuming h is non-zero, then 5/4 h is equal to 18, which means that h is equal to 72 fifths. And again, we want our answer as a decimal to the nearest tenth, so it's good that we have a decimal answer. And this will be equal to 14.4. So, I feel like this way is pretty fast. If you were doing the trig way, if we were doing like 180 degrees minus an angle,
Well, you could just do. You
um,
could add the two angles together and then minus them.
add them and then minus them. What?
Yeah, add the two
What
angles
do you
together
mean?
and then minus like the angle. Like find 2a first and then do 180 minus 2a.
But you need the sine and cosine of 2a.
Oh, right, that makes sense. Yeah. So I mean,
So you
yeah.
yeah, here you would have to use the sine difference twice. Actually, wouldn't even or actually I think that's good. But you have to use it twice. And that would be a long expansion. And I don't know, it'd just be kind of long. Um it's just the thing to notice here is the similar triangles here. And then you can make ratios and then you can solve it, put it in a quadratic equation. And with 3D geometry, the big thing is that you always want to put it into like a simpler 2D case. Um, or I don't know. It's just you want to put it in 2D, and then you want to use a bunch of tools on that 2D thing, and then hopefully you can solve some stuff. Um, yeah. Okay. Oh, is our answer correct? Uh, yes, it is 14.4. Okay. I need more space. I'll use this space right here. No, that's not enough space. No, I ran out of space. Well, let me try making my brush smaller, and we're just gonna zoom into this.
I think you should just get rid of your work often.
No, that's too. No, it's good. It's good. Let's see what I can. See, I'm just gonna make my stroke like here. I can set it down. Now we're gonna be at 0.25. Right? So now look how small it's gonna be. It's gonna be really small, and then we just zoom in. So now we got a bunch of space. See, and the brush size is fine. See, so that's called making more space in no space. Okay. Okay. The circle O as shown. OP is 2 units. PL is 8 units. PK is 9 units, and NK is 18 units. Points KP and M are collinear, as shown. Or no, never mind. As are points L, P, O, and N. What is the length of segment MN? Okay. You're gonna have a diagram on your test, but I'm gonna have to draw this. Or unless actually, I could probably just screenshot this. Um, no trackers. No. I'm gonna try it on here. Oh, oh, it works. Okay. Yeah, here's the diagram. Okay. And let's just go ahead and label everything that we have. Um, so this is 2. My disk is almost full. Okay. Why? See, my stroke, my brush thickness just randomly reset for no reason.
I have never used this. I don't know what it
I just I added a screenshot and it reset. See,
I
that's
don't know
why.
what the
Okay.
problem is.
Wait, look, it reset again. It's on 1. I literally just put it onto 0.25. Look, look,
Maybe
look,
it doesn't
look.
accept decimals.
No, it was working before. See, look, now it works.
I
See
don't
what?
know.
Okay. Oh, Adobe Illustrator. Okay. OP is 2, PL is 8, PK is 9, NK is 18. These points are collinear, these points are collinear. Okay. You wanna see what we can do on our diagram here. Okay, one thing you can see is that the radius of our circle will have to be 10, right? Because OP is 2, PL is 8. That means the radius of our circle is 10. That means you can also go ahead and label ON as 10. And then so PN will be 12. Okay, so that's pretty useful. Gets you another assignment. Okay, think of what else you could do. You know, you see a bunch of crosses in a circle. Maybe you think of PowerPoint. My disk is almost full. I know. Oh my god. Okay. Okay, so you see a bunch of crosses in a circle. So you could think of PowerPoint. So we could try PowerPoint. The only point where you could utilize PowerPoint here is P. So you know we can use PowerPoint here to find PM, the length PM. Maybe that will help us here. Maybe it will not, but you know we just want to get more information on the board. So so we're gonna have 12 times 8 is gonna be equal to 9 times PM. So then we're gonna have 12 times 8 over 9, which is 4 times 8 over 3. So this is 32 thirds. Oh, also, it says what is the length of segment MN, right? It doesn't say what is the length of segment MN to the nearest 10 or to the nearest 100. So if it just says that, again from experience, like usually like it's wanting an integer, and if you don't get an integer answer, you should try like just briefly checking your work again. And also like usually when it just asks this, usually it does not want a fraction either. Usually if it wants a fraction, it will say what is the length of oh what the heck? Oh okay. Okay, yeah. But if it just says this, what is the length of segment MN? Usually it doesn't want a fraction either. Um usually if it wants a fraction, it will say what is the length of segment MN expressed as a common fraction, or expressed as um, a fraction in simplest radical form or something. Um, so yeah, if you see this, just know that it very, very most likely wants an integer answer. If you don't get an integer answer, you should check your work. Or you know you could just like put what you got just for now, but like put a star next to the question, and once you like finish through the whole test and you have some time left, you want to go back to this question and just check your work. Okay. Anyway, so now we know that this length is 32 thirds. Okay, that's fine. Um, we want to sorry, want to find more information. Um, want to try to get more information onto you. One thing you can find is that triangles KNP and LMP are similar. Why? Because angle K and angle L are the same angle. Why? Because they are both on the circle, both points on the circle, and they intersect the same arc. So they had to have the same angle. And these two angles are the same just because they are vertical angles. Then these two triangles are similar by AA. Then we can find what the length of this side is, right? ML, because we have a ratio here, 9/8, and we have this long length. So then we can find what ML is. So we could say 9/8 is 18/ML. What the? I drew a radical sign for some reason. Okay. So then ML is equal to 2 times 8, which is 16. Okay, so that's good. We have more information on the board. But we want to find some more stuff so that we can relate these sides to MN, which is what we want to find. The crucial thing to notice here is that NML is a right angle. It's a right angle because the arc NL is 180 degrees, and M is on the circle and it intersects this arc, which means that its angle will be 180 degrees halved, which is 90 degrees. So this angle will be 90 degrees and it will make a right triangle. So the thing to always remember is that if you have an inscribed angle on the diameter of a circle, that angle will always be 90 degrees. And it will be helpful in a lot of cases because 90 degrees, you can utilize that on right triangles and whatnot, right? So yeah, just generally be on the lookout for that if you're working on circle geometry problems. So now that we have this right angle, this is going to be extremely useful, right? We know that this whole diameter, NL, is going to be our radius times 2, or 20. Or we can just add all that up, right? And we found before that ML was 16, right? So then all we had to use is Pythagorean theorem to find what MN is. And we have 20 and 16. 16 is 4 times 4. 20 is 4 times 5. We can see that this will make a scaled by 4, 3, 4, 5 right triangle. So then this will have to be 3 times 4, which is 12. Now we can see that our integer was an integer which was predicted from it saying just what is the length of segment MN. So we're good there, and that is our answer. Anything you want to say there, Bill?
I mean, not really. This problem is very tempting to do PowerPoint on, but there's not really a point to doing it.
It's tempting to what?
It's not really
PowerPoint.
A point to do PowerPoint.
No, I think if you notice PowerPoint, you should just go ahead and use it just to find the length of the side, and maybe it will help you later.
Yeah, just to give you more information. Yeah, it's normally fine if you do it.
Yeah.
I was kind of surprised this problem didn't use PowerPoint, given like it looked like this.
Yeah. Okay. Next question. So look at how much space we have. We have infinite space. Okay. Consider the sequence 1, 2, 3, 4, 5, 6, 7, 8, 9, 19, 29, where the sum of the digits of a sub n, the nth term, and a sub n plus 1. Oh wait, sorry. Where the sum of the digits of a sub n, the nth term, is equal to n, and a sub n plus 1 is the smallest positive integer such that a sub n plus 1 is greater than a sub n. What is the value of the 25th term of the sequence? Okay, First thing it's saying that every term, every nth term, the sum of its digits is equal to n. So you can see that you first have a list of digits. Those digits summed is equal to n, which is itself, but yeah. And then on 19, this is our 10th term, right? And 1 plus 9 is equal to 10, just like it says. Okay, and then the second thing is that it says is that our sequence is increasing, but we want each term to be as small as possible, but so that it is still increasing. So like, you know, on a 10th term, it can be a ton of stuff, right? It can be 19, it can be 109, it can be 1000009. But we want it to be the smallest integer such that it is larger than 9. And that would only work with 19. So that's why it's in our sequence and not anything else. And with this, we want to find what's the value of the 25th term of the sequence. Okay. Maybe we should just try listing some more terms out just to see if we can find a pattern, right? Right now, we don't really know much. This is not a sequence that we are familiar with. So you just want to try to experiment with thinking some stuff out. Okay. So, we have 19 and 29. This is our 10th and 11th term, respectively. Let's think of our 12th term. It has to be greater than 29, but we want to make it as small as possible. Now, the 10th digit will have to be either 3 or greater, right? Because this integer will have to be at least 30, right? Because it has to be greater than 29. So our 10th digit will have to be at least 3 or greater. Now we want it to be as small as possible. So why don't we try using the 10th digit of 3? Well, if we use the 10th digit of 3, and the sum of these digits have to sum to 12, then our unit digit has to be 9. Okay. So then from that, we just know that our 12th sequence number is 39. And then, if we look on the 13th, again, our 10th digit is going to have to be 4 or greater. And let's just use 4 to assume to get the smallest it can be, right? But then, because the digits have to sum to 13, then this would be 9. And this would be the smallest, right? Because we set it to 4, the 10th digit to 4. So you keep on going like this, and it will just always go like this. So like 29, 39, 49, 59, all the way to 99. And we can figure out what term this is by summing these digits, right? This is the 18th term. Okay, so this helps us out a bit, right? Because gets us closer to the 25th term, right? And this is, as we're going with this is looking more like a list out sequence to get to the 25th term instead of like some pattern, like some algebraic pattern, and then using formulas to find it, right? Because because this is not like a very algebraic sequence, if that makes any sense. Like it's not a great one to put into a formula, and we're already at the 18th term, so we're not far away from the 25th term, so we can just list out a few more terms to get to the 25th term. Okay, so now let's think about the 19th term. Digits have to sum to 19, has to be greater than 99. We want it to be as small as possible. Okay, so it's going to have to be at least 100 or greater. Let's just have our 100th digit as 1 for now, because we want to make it as small as possible, right? Then our other 2 digits have to sum to 18. Well, if we have 2 digits that sum to 18, there's only one way to do that. And that one way is to have both of the digits as 9 and 9. And this is going to have to be the smallest integer that satisfies this, that is greater than 99, right? Because we said this was 1. 1 would be the smallest the smallest way we can have it, right? It has to be 100 or greater. 100 digits has to be 1 or greater. We're saying it's 1 to find the smallest. And then we find only one case, and it has to be the 99. So then this has to be our number. Okay, now let's think of the 20th term. Now, it has to be greater than 199. It has to be 200 or greater, right? So it's hundreds, it has to be 2 or greater. Let's just say it's 2 to find the smallest it can be. And then the two other numbers would have to sum to 20 minus 2, which is 18. But the only way to do that is 99. But you see that this will keep on going. It's going to be 99, 199, 299, and then 399, 499, 599. We can just keep on going like this until the 25th term. And that is going to be on 799. We know that because this sums to 25. So then this is going to be our answer. That is our answer. Okay, so when I solve this, seems a bit like a long problem. But honestly, when you solve this on yourself, like all this, you should be thinking in your head like much quicker and just like when you're solving this by yourself, it should take like a lot quicker than me like trying to explain every detail like really logically. I don't know. But yeah, anything you want to say there, Phil?
Yeah, just like list them out. Don't try to actually like find a representation for them. Even if there were a representation for them, this is the 25th term. Unless it's a really bad sequence, you should probably just list it out. Not that bad.
Or wait, this will be repeating like like you get to 999,
Yeah, you get to
and then
999.
it's gonna be like
One nine. Yeah,
1999, right?
yeah.
Yeah.
It just means
Wait,
one nine.
is there a way to like put this in a formula? I don't know.
Generalize it? I wouldn't
Yeah.
say. I wouldn't say there is.
Or I mean, you could put it in like a what is it? It's like a partial function. It's like um you have like I can't I need like curly bracket. Okay. So like if x is oh C will be shown. Okay. What if x is less than or equal to 9, then it's just gonna be x. If x is less than or equal to 18, then it's gonna be it's gonna be then it's gonna be x minus 9 times 10 plus 9. And then you can just keep on going with that. But yeah, but there's probably not a way to like do it like without partial stuff. Okay, but like uh basically just know that like for sequences, if you want to find some end term, it does not always have to be like you find a generalized formula for it, and then you solve for that end term. It could definitely be like you just list out stuff to get to that end term. Yeah. Okay. It's 8:28. Guess we're just gonna end here. My voice is also pretty dying.
Okay.
No. Okay. But okay, so yeah. We will continue here. From our next meeting. And if you guys want to request us for doing a year, just let us know. I guess for now, we're just going to continue going up. So after we finish 2012, we'll do 2011 and 2010 and so on. But if you guys want us to do like earlier years that we haven't done, like 2020, 2019, or 2018, just let us know and we could probably do those as well. Okay, but that's it. Thanks for watching and see you guys next week.